Professor Cummings, and I'm going to start a new topic here. It's still in the Strength and Materials playlist, but just changing it for a different problem or a different aspect of Strength and Materials. And what I wanted to start off with was asking the question, how would you go about designing a drive shaft? So how is a drive shaft actually designed? And what I mean is, what kind of questions would you have to answer before you approach designing a drive shaft? Meaning what type of properties should that material have? How hard should it be? How ductile should it be? How rigid should this material be? And what difference does that make? Does it matter whether you got a drive shaft made out of cast iron or a drive shaft made out of brass? Second is, does it matter if that drive shaft is hollow or solid? Are there certain advantages to either one of those? And is there a particular situation which you want one? And what difference does that make in the design? And lastly, what kind of load is this drive shaft going to be under? If you had to describe this load that the drive shaft was under, as you can see this thing rotating, what type of loading is that the drive shaft is actually dealing with? First, let's look at a drive shaft. So this is just one type of drive shaft in an automobile. And as you can see, it's a kind of a basic picture. You got the engine over on the left, and the arrows going from the engine to the wheels, and all through that center is the drive shaft going to the rear wheels, from the differential into the rear wheels. So what does that drive shaft actually do? In the most basic engineering terms, what is that drive shaft doing? What act is it performing, and how are we going to design around that act? Okay, so what it does is, it actually transmits power from the engine to the differential. Actually, transmits power from the engine to the differential, which transmits to the wheels. And in the front, it just looks like that's going straight to the wheels, but it actually transmits power. The drive shaft, it actually controls the speed of the wheels. So the drive shaft actually transmits, or whatever that rotational speed of the engine is what goes into the transmission. And the transmission obviously is missing in this picture, but that's what's actually dictating the speed of the wheels. It also applies torque, into the drivetrain. So the torque that's being imparted by the engine is what's being transmitted on through to the rest of the system. So the drive shaft has to be designed to efficiently transmit power, speed, and torque from the engine to the rest of the drivetrain. So that's the primary purpose of that whole drivetrain. So it's just a transmission of power, speed, and torque. All right. So what happens when something's under a torsional load? What is a torsional load? A torsional load, is what the drive shaft is actually under. This is called a torsional load. You're actually imparting a torque onto the drive shaft or onto a material, causing a rotational force. So it's actually going into a torque. And just to define torque, here we have a circular area, I call it a shaft, or you call it the end view of a shaft, and you have got a force being imparted on the shaft, and it has a certain radius, and this is what's called a torque. So the force is going around a center axis, and that is imparting, or what is calculated to be, a particular torque onto that drive shaft. So force is applied to the shaft, and it creates this torque. And the way you can look at this is that the torque is the force times the radius of the shaft, or torque is also a function of the power divided by the angular velocity. So the more power the engine has, the higher the torque. The higher the angular velocity, then has the lower the torque comes on the engine. But it's a function of both the power and the angular velocity. So that's going to be very important in understand what's going on, part of what's going on with this engine, or this drive shaft. So this is part of what kind of load this is under. Now, as you have a member or a shaft under a torsional load, you can see that it's actually going to have a bit of a twist going on to this torsional load. Now, this torsional load is actually, if you take a small differential, a small area of that drive shaft that's getting put under torsional load, what you'll find is that the member, a small differential or a stress element, is actually under a shearing stress. So the twisting of the member develops a shear stress. So this is actually the load going one way, and it's actually got a resistance inherent to the material going back the other way, and that's creating a shear stress. And shearing stress, just like normal stress, is force over area. In this case, the area, cross-sectional area of the drive shaft. So that shearing stress is force over the area being the area of the drive shaft. So that's also something to keep in mind as far as what this drive shaft is under. So a key part of actually designing it. Now, what else has happened under this torsional load? Well, we saw that it's under a twisting motion. So if we take a shaft and we have a random point on this shaft, we'll just call it point A. And this is, we're looking at it a cross section, the lengthwise of it, and we do have a torque applied, or a torsional load applied to this shaft. What you're going to notice is that there's going to be some deformation. We spoke about deformation in axial loading, but deformation also takes place in torsional loading. So there will be some deformation angularly going, and it'll drive from point A over to, say, A prime, and it will create this angle where it actually would deform through, and instead of delta, which would be linear deformation, angular deformation is represented by phi. So the beam, or the shaft, is going to deflect under that torsional load, and that's what's known as the angle of twist, and this is in radians. So angle of twist is the way this load's going to start to deflect angularly. And it's going to go through, and that's just a cross or a lengthwise view of the same phenomenon. And the nature of that load, or the nature of that deformation, is going to be based on the shear modulus of the material, which is just a ratio of stress over strain. Analogous to the Young's modulus, and the length of the beam. So as you can see, the longer the beam, the more likely you're going to get some sort of twist versus a short stubby beam. You're going to have a little more resistance there. So the angle of twist can be calculated based on that shear strain, the length of the load, and the radius of the load. And the shear modulus is the stress over strain. So we're looking at something that's still within the elastic region of the stress strain curve. So we can see there is some matter of material. So this is the reason you don't see a lot of cast iron drive shaft on sports cars. You do want to have some level of flexibility in a in your beam, as well as you have to take into account the length of the beam as well as the radius of it to dictate how much of that angle of twist is going to take place. So how do we keep that shaft from failing? Why doesn't the shaft fail? Why aren't we seeing tons of these sorts of conditions taking place where a shaft just literally wraps around itself like a rag? It actually wraps around itself like a rag, having a failure underneath the car. Well, there's a few things that can be designed to take that into account. There's something called the polar moment of inertia. What this is just a measure of a beam or a shaft's ability to resist torsion. So its ability to resist just twisting in on itself. And it's based around the z-axis. You can go another video onto the polar moment of inertia, the real mathematics behind it. But it's based around the area and the twisting or the torsional force going around the z-axis of the shaft. So this is totally dependent. This polar moment of inertia is totally dependent on the shape of the beam. So you'd have a different polar moment of inertia if you had a I-shaped beam, a square beam, a triangular beam, versus say a round beam, or even a beam that is, or a shaft that is hollow. So a solid round shaft, circular shaft, versus a circular shaft that's got a hollowness to it. And in this case, looking at circular shafts, if it's hollow, it's based around pi over 2 times r to the 4th. It's the polar moment of inertia. And if it's hollow, we've got to take into account that it's got an inner radius. This is what r sub I stands for. R sub O is the outer radius, R sub I is the inner radius, and we're subtracting the material that is not there. right? So the polar moment of inertia on a circular beam. So this is how much, one way we can understand how this is going to resist the torsion. Now, how do all these things that we went over just relate? How does the polar moment of inertia, the stress, the shear modulus, the radius, all these things, and the length all relate to each other? Well, let's review some of the questions. So we got the torque. We know that the torque is a function of power over the angular velocity. So that's taking into account what the engine is, what the engine is putting out. So the power and its actual speed. We know that it's going to inherently create a shear stress because we're creating a torque, and therefore there's going to be a shear stress. So it's a force over the area. We know there's going to be an angle of twist, and that angle of twist is going to be a function of the shear strain, the length, and the radius of the shaft. And the shear modulus comes into play, and you can see a direct relationship with the shear strain, stress over strain, and this angle of twist. So these two can actually be related if you solve both for the shear strain and relate these two concepts together. And then there's the polar moment of inertia, so the resistance to torsion. And if you put these together, through some algebraic relating, and you can see this is what's known as the general torsion equation. So it's just saying the ratio of the maximum shear force, shear force to failure, to the radius is equal to the ratio of the torque to the polar moment of inertia, which is equal to the shear modulus times the angle of twist over the length. And with this basic equation, we can actually derive, algebraically derives other equations that are going to be important to the design of a drive shaft. So how do we get from that point of wondering how that drive shaft should be designed, what we have to take into account, and using this general torsion equation for circular shafts? Well, one thing we can actually gain from this is understanding how to select the material. If we know what the maximum shear stress is, based on this, and we know what our concern is with failure, we can actually use this equation to actually help understand what the maximum shear stress should be, or what we can design to, what torque we're actually going to expect based on the amount of power and the rotational speed. And from there we can actually start to figure out what the polar moment of inertia or the inner diameter. So this particular equation is really important to understand, and you can see the benefits of a hollow shaft to a solid one. Of course, a solid shaft will have the same outer diameter, will have a somewhat more resistance to a torsional load, so resistance to being twisted. But a hollow shaft will actually have less weight. So this could actually become an important design factor that you're concerned with, and through the polar moment of inertia, you can understand, actually see that in your design. Another thing is understanding how the shaft's going to become deformed. Understanding the torque, the length that you have to design to, and the polar moment of inertia, and the shear modulus of the material, which also goes into the material selection. You understand the deformation that shaft is going to go through, as well as the superposition of the shaft if you have any type of complex shape. So if the shaft changes geometry anywhere along the way, if it has to be tied to a separate material, or if you have multiple torques, if you have a gear train or a shaft that's going to have several gears on it, you can actually decide, understand what type of distortion or deformation you're putting that shaft through. So this is the basics. So we'll be a few more videos going over the torsional equation and just torsional loading. Do a couple of examples. So if you go ahead and subscribe to the channel, ring the bell or smash the bell, whatever that the lingo is on that one, I'll go ahead and start uploading videos, a couple of these a week, as I go work through this series on strength of materials. All right, this is Professor Cummings. I'd like to thank you for tuning in.